Welcome back to Polymeric Biomaterials. In the last lecture, we have started looking at the theme of biomaterial processing, under which we looked at a few different techniques to process polymeric biomaterials into implants and shapes. We looked at melt extrusion, we looked at injection molding, compression molding, fiber spinning, and so on. And we also had a chance to look at some design considerations when it came to scaffolds. Now, in this lecture, what we'll do is we'll take one particular type of processing technique, namely polymer electrospinning, and we will try and dig deep into this particular technique to try to understand various dimensions associated with biomaterial processing. So, with that view in mind, in today's lecture, we will first start off with some comments on some historical aspects of electrospinning and the fundamental forces involved. We will next take a look at the operating conditions that are involved in electrospinning and how those affect the process itself and the resulting fibers that form. Then we will approach electrospinning from a polymer solution perspective, which is to look at revisit some of our concepts in polymer solutions and then look at how they can impact what we call electrospinnability. And related to that, we will also look at solvent quality and chain entanglements and their role in promoting fiber formation in electrospinning. And then we will look at actual videos of the cone in electrospinning and the jets that form, and focus a little bit on the types of cone shapes you can get in electrospinning. And then we will towards the end move on to some practical aspects, namely configurations in electrospinning and maybe geometries in electrospinning for collectors, and then look at how those impact fiber and mesh properties, and finally end with maybe one quick slide on some end use cases. So, with that quick background, let's jump right into the lecture. And we will start off with some historical aspects, some comments on that. Electrospinning is a very popular process today, but it's by no means a very new process. So, shown here is a timeline of some key aspects associated with electrospinning. So, in the 1880s, we see that Rayleigh had conducted formal investigations on instabilities in electrically charged liquid droplets and had looked at breakup. In 1902, Cooley and Morton, of course, they filed independent patents describing the use of electric fields to produce fibers from liquids. But it wasn't until 1934 that Formhals patented the first working electrospinning apparatus, which enabled continuous production of fibers. And then in the 60s, G.I. Taylor, built the theory for electrohydrodynamic jetting and cone formation for liquid droplets in the presence of an electric field. And the cone that we see in electrospinning, as described by Taylor, which has an angle of roughly 49.3, the semi-vertical angle of 49.3 that Taylor showed, is named after him and is popularly called the Taylor cone. And thereafter, there wasn't much practical use or interest for electrospinning after Taylor's work. The technique itself, electrospinning technique itself, didn't have a lot of traction until the 90s, when the process was essentially rediscovered by Renneker, Yarin and others, to the point where now, 30 years later, the field has just boomed. You will find thousands and thousands of research articles on electrospinning, right from fundamental aspects of the processing itself, all the way up to the use of the resulting nanofibrous membranes for various applications, including biomedical engineering. One quick comment about Professor Renneker, who passed away in 2021. Some of his early work, in fact, a lot of his early work was in industry and in government labs in the US. Where he worked on fundamental problems in polymer physics. But in the late 80s, when he was close to 60, he joined the University of Akron, and that's when he started working with electrospinning. And over the next 30 years, boy, did he change the field completely, right? So he essentially rediscovered this process and put out a series of seminal papers that essentially changed the way people thought about electrospinning and the use of electrospun meshes. A very, very inspiring story for someone to start working on this when he was close to 60, and until about 90, the next 30 years, he continued to put out exceptionally high quality work on various aspects of electrospinning. A lot of what we understand today about electrospinning comes to us from Professor Renneker and many others shown on the slide who have contributed to this field before him. So with that quick historical perspective, let's move on to looking at the guiding principles and the forces involved in electrospinning. So electrospinning is a fiber spinning technique, right? We have hinted at this in the earlier lecture, and we looked at fiber spinning, where we saw that there was a requirement for a spinneret, but in electrospinning, the driving force is an externally applied electric field, right? So electrospinning occurs when electrostatic forces that are induced due to the applied electric field overcome the intrinsic surface tension of the polymer droplet, whereby repulsions arising from the charges stretch this polymer solution into a jet, right? And that cartoon is shown here. So what you have is here is a spinneret through which a polymer solution is flowing at a constant flow rate. It's pumped at a constant flow rate, at the tip of this needle, which is typically a metal needle, a very high electric potential is applied of the orders of thousands of volts, 10-15 kilovolts if you will, and that leads to deformation of the droplet that was initially largely held by surface tension in the form of a sphere into a cone-like shape, and then the emanation of a jet from the tip of the cone, and that is shown here, where if you have no voltage applied, you largely get a droplet for the polymer solution, and this keeps dripping. But as you apply voltage and you keep increasing the voltage, you now have induced charges, and eventually when the electrostatic repulsions overcome the surface tension, and that's the key in electrospinning, you start to get this jet that emanates from the tip of the cone. Now, if you have sufficient chain entanglements, and we will see quite a bit about that later in this lecture, that offer viscoelastic resistance to suppress the breakup of the droplets, leading to formation of very thin fibers for continuous fiber formation. And the jet that forms here as it comes out undergoes a series of instabilities here before collecting on a grounded metal collector such as a drum collector shown here. Later we will talk about collector configurations, but in a quick snapshot, this is what electrospinning is. So in summary, you're thinking of a polymer solution. It could also be the melt. In this lecture, we're largely focusing on solution electrospinning, but many of the concepts that we're going to look at here will equally apply to electrospinning from melts. But nevertheless, so what you have here is a polymer solution that's being pumped out through a metal orifice such as a needle, and a very high electric potential is applied to the tip of the needle as it comes out. And if you keep increasing the voltage, the field strength, what's going to happen is that's going to result in deformation of the droplet that was originally held by surface tension. At some point, the electrostatic repulsions overcome the surface tension, pulling the or deforming the droplet into a cone, and a jet emanates, which then undergoes a series of instabilities and finally collects on a collector which is grounded, right? And under electron microscopy, SEM, what you will see is a structure that looks like this. So it's a what you would call a non-woven fibrous mesh. Now, if you recall, in the previous lecture number 27, we looked at the process of fiber spinning and then post processing using knitting, braiding, etc. Right? In contrast to that, this technique directly gives you a fibrous mesh, but these are non-woven. That's a very key aspect to keep in mind. Now let's look at this process in some more detail, and we will look at the different parameters that affect electrospinning. Right? Broadly, they are classified into what you would call solution parameters, operating parameters, and ambient conditions. And shown here is a schematic of the same electrospinning process now in the vertical configuration. Earlier, what we saw on the previous slide was the horizontal configuration, and one can operate with both depending on what one's interest is. But shown here is a vertical configuration. You still have the needle, the metal orifice through which the polymer solution is pumped, and then you apply a very high electric potential here, right? One of the key things to keep in mind in electrospinning is, if you're talking about solution electrospinning particularly, there is a requirement to have a separation distance between the tip of the needle and the collector. And this does a lot of things, but one of the primary things it achieves is it gives the polymer solution the time to completely evaporate the solvent. So, the solvent evaporates during flight. Right, over this distance, and a lot of the drying and thinning happens. So, two things happen here. As the solvent evaporates, there is drying, but the jet is also thinning, right. So, drying and thinning happen simultaneously, and we can talk about different regions in the electrospinning setup itself, which we will talk about later, where you can have different magnitudes of drying and thinning. Ultimately, when the fibers hit the collector, most of the solvent would have evaporated. If all goes well, you should get a fairly dry, non-woven fibrous mesh on the collector. Now, this is a fairly complex process, as you can clearly see from the number of operating solution and ambient parameters that affect the process, and this was just a snapshot, mind you. There are many more factors that affect electrospinning, but this was just to give you an idea of what kinds of factors are involved. Now, one of the first things you can think about is polymer concentration, right? This is the volume fraction in solution, and like I said earlier, if you don't have enough entanglements in solution, and then you're going to have largely electrospraying that happens and not electrospinning. Essentially, if there isn't enough polymer volume fraction or concentration in the solution, and this can be benchmarked against the entanglement concentration, which we will look at in just a bit, then what you will end up, if you are well below that concentration, you will end up getting something called electrospraying as opposed to electrospinning, which will give you droplets. So, polymer concentration plays a very important role in electrospinning. Solution conductivity also plays a very important role. As you can appreciate, if I keep increasing the solution conductivity either through the correct choice of solvent or through the addition of conductive carriers, I can have more and more charge carriers in solution, which is going to lead to higher stretching, which is going to directly affect the thinning of the fibers. Right? That's something that you can easily appreciate. Solution viscosity has to be tied to polymer concentration and the molar mass. And like I have already said, if you don't have enough chain entanglements, and if you are well below that, what you are going to end up getting is electrospraying. You have to have sufficient entanglements in solution to ensure that the polymer solution that's being stretched is able to resist breakup and form these thin, elongated fibers in a continuous manner. Solvent properties also play a very important role. Two very important properties of the solvent that play a very important role are the vapor pressure as well as the dielectric constant. Right? So, solvent property is just an umbrella term for a large number of properties you can look at. Of course, we are not even talking about the solvent's ability to dissolve the polymer, which comes from something like a Hansen kind of an analysis, right. So, vapor pressure, just as a case in point, you can imagine that as the electrospinning jet goes from the needle to the collector, one thing I have already mentioned is that the solvent has to evaporate, right. So, if you have a solvent whose vapor pressure is extremely low, right, then that's going to lead to issues because you will not have enough drying that happens. So maybe you have to use a very large tip to collector distance, that is the distance separating the needle and the collector, or you have to use very low relative humidities. So you see that some of this is also related to things like this and this. Of course, another important property of solvents is the surface tensions, right? Water has a very high surface tension. So water-based electrospinning is typically not that easy because of the very high surface tension and the very high dielectric constant for water. So these are some aspects that have to be carefully studied and examined before one starts to look at electrospinning and electrospinnability. That is from the solution parameter perspective. Now, if you move on to operating conditions, broadly one can think of three main operating conditions. The voltage and the tip to collector distance together can be thought of as one parameter called electric field strength, which is simply V over T. That's one way to think about the combined effects, and it's been now quite well established that there is a coupling that exists between voltage and tip to collector distance, which dictates the electric field strength. Of course, electric field strength decays from the tip of the needle to the collector. So where you place the collector not just determines how wet or how dry the fibers will be when they hit the collector, but it also directly affects the electric field strength and the electric field line distribution. Flow rate also has a very important role to play because you are pumping out or pushing out polymer solution, and you are also continuously applying a voltage to sort of stretch it. So there is a balance of these factors that has to be struck to get fibers that don't have defects, and we'll talk about some kinds of defects that you can possibly get in these fibers. Of course, collector geometry also plays a very important role. So shown here is what you would call a static or a flat plate collector, where once the fibers deposit, you will get fibers that don't have any particular direction of orientation. So you will largely get a fibrous mesh where the fibers are randomly oriented. But you can also have a drum-like collector where if you rotate the drum really fast, you can now align the fibers in the direction of drum rotation, and that can have specific implications for how you can use them in specific kinds of biomedical applications. And then of course ambient parameters, as we have already hinted at, humidity plays a very important role, relative humidity, because it has to be sort of matched against the vapor pressure of the solvent. If you are using water-based solvents, there is another interesting, or aqueous solvents like water, there is another interesting thing that could happen is because the solvent is also water, the relative humidity can have a very large influence on electrospinnability of such systems compared to solvents that are not miscible with water, right, with relative humidity. So these are some aspects to keep in mind as you think about the process of electrospinning, right. So you see, this, while it appears like it's a fairly straightforward process to create nanofibers, as they are typically called in the literature, the process itself is extremely complex with a very complex interplay between solution parameters, operating parameters and ambient parameters, all of which have to be carefully studied as you start preparing for making electrospun meshes for specific kinds of applications. And in the context of biomedical engineering, in a course like this, polymers that are typically electrospun and widely reported in the literature include your standard polyesters. So these are all degradable polyesters that we have seen. You can also have polyurethanes being electrospun. You can have polyvinyl alcohol being electrospun. You can have PDO, which is another very important biomedical polymer. You can also have natural polymers such as collagen, gelatin and chitosan. And there are some very interesting challenges in processing polymers like these because these are charged polymers, right. And so one of the from a processing perspective, because we are looking at this in the context of biomaterial processing, from processing perspective, electrospinning of these charged polymer solutions becomes a bit tricky because particularly polymers like chitosan, right, where it's a polycation or alginate, which is a polyanion. polymers like these, what are called polyelectrolytes, are harder to electrospin because the charges on the polymer will repel in solution, preventing chain entanglement. So what will happen is you can keep increasing the polymer volume fraction in solution. That will lead to an increase in viscosity without concomitant increase in chain entanglements. But again, from a structure property perspective, these are some important aspects to keep in mind as you think about processing some of these polymers through electrospinning. Now, that's a good segue for us to now look at polymer solutions and the idea of electrospinnability, right? So we have already hinted at the fact that you're looking at solution electrospinning, for which you need polymer dissolved in a solvent. And dissolution is something we have already looked at in great detail in lecture 14, polymer dissolution, and we have looked at solvent quality in lecture 9 in great detail. So some of those concepts have to be sort of recalled at this stage for us to proceed with the discussion. So firstly, we note that this dissolution is dependent on polymer solvent interactions. So the chain conformation in solution is affected by the solvent quality, whether it's a good solvent or a poor solvent, and the nature of the polymer solvent interactions and the temperature affect the solvent quality, right? And we have already seen in lecture number 9 that chains in a good solvent, a real chain, right? The scaling is 0.6 roughly, 0.588 to be more precise, or the scaling in a poor solvent happens to be 1/3, which is the collapse chain. And shown here are cartoons of what the chains would look like in a good solvent, heater solvent, and a poor solvent. And obviously, what you want for electrospinning is a good solvent. You want the solvent to solubilize the polymer so that you have a homogeneous solution that you can process through electrospinning. Now, from an interaction perspective, one way to think about a good solvent, or from a miscibility perspective, one way to think about a good solvent is to resort to what you would call a Hansen solubility approach. Now again, recall that this is not something that is new. We have already looked at Hildebrand parameters in lecture number 14 when we looked at polymer solutions. We are just building onto that by looking at Hansen parameters. Now Hildebrand, if you recall, is largely for van der Waals kind of dispersion forces. It cannot account for polar interactions, it cannot account for hydrogen bonding, etc. And that has its own limitations. But if you now look at Hansen solubility parameters, which is largely an empirical approach, and that's something that you have to keep in mind. Hansen is primarily empirical, right? But that doesn't make it bad. It still works very well for many systems, but it's just something you have to note. And Hansen, in some cases, arguably, is a significant improvement over Hildebrand because it now accounts not just for dispersion, but also for polar and hydrogen bonding interactions. So it has 3 components, and for looking at whether a solvent is a good solvent and whether it's miscible, again the idea is like dissolves like. That's the basis for all these kinds of solubility parameter approaches. In Hansen, what you're doing is the polymer defines the center of a Hansen solubility sphere with interaction radius R0. So if you think about the polar, hydrogen bonding and the dispersion forces, you can now define something called a Hansen sphere for a polymer R0, and you can now think about where your solvent lies in relation to the radius of that sphere R0, right? And that is given by something called a relative energy difference, RED, which is simply R sub A over R sub naught, where R0 is the maximum value for a good solvent. So R0 you can determine experimentally. You take a series of good solvents and you find out the maximum value that encompasses what you would call a good solvent for that particular polymer. That's given by R0, and then RA is your solvent of interest, and that distance is between the solvent and your polymer. So now what you are asking is, if RED is less than 1, in other words, if your solvent lies within the Hansen sphere like so, it will be a good solvent, and if your solvent lies beyond the Hansen sphere, it's a poor solvent, or the system will be immiscible. The polymer will not be miscible with that particular solvent. So this is sort of a in some sense a simplistic way to think about polymer solvent interactions, but it works very well for many systems because now it accounts for all these kinds of interactions, right? And you can find Hansen solubility parameters in standard handbooks, and those are quite often used for determining, at least first pass, what kinds of interactions exist between the polymer and solvent in terms of doing calculations such as the RED. Another way to think about it is simply to look at the difference between the solubility parameters for this polymer and the solvent. I mean, there are standard rules of thumb for these things. If the difference is less than a certain number for your interaction parameter, then it's likely to be miscible. If it's above a certain number, then it's likely to be immiscible. Again, the idea is the same. Overall, what we are saying is the closer they are, the more favorable the interactions. Thus, it's likely that this will be a good solvent for the polymer, and that's a prerequisite because polymer solvent interactions influence the polymer solvation and solution viscosity, which directly govern electrospinnability. So, it's very important to keep in mind that this kind of an approach can tell you something very important or very meaningful about whether the polymer will dissolve in that solvent or is miscible in the solvent, and what kind of interactions can you expect and how that directly affects the solution viscosity and solvation, which in turn affect the electrospinnability of the polymer. Now, continuing on this discussion, you can now think about the fact that you have identified a good solvent and you have dissolved the polymer. Now, what else determines electrospinnability? Is that the only requirement? No, there are other requirements from rheological perspectives, and just to give you a hint, we are looking at two different perspectives. One is shear, where I've already hinted at the fact that if you don't have enough chain entanglements in solution, you're going to have breakup of the jet into droplets. So, polymer chain entanglements are very critical, and those can be sort of gauged using specific viscosity measurements, which ultimately governs electrospinnability, right? And we will look at some examples of that. Another way or another rheological perspective to look at is extensional rheology, where if you have identified a solvent and if you have the right kind of operating conditions and the right kind of chain entanglements, you can now form stable jets. But then remember that this is being stretched. So, you're looking at extensional flows here. And so, what becomes important here during the electrospinning is extensional viscosity. So, specific viscosity, G prime, G double prime, these kinds of things may govern whether the system is electrospinnable or not. But during electrospinning, what becomes very critical is extensional viscosity, relaxation time, and we've already looked at the Deborah number in lecture number 24 and 25, and elongational strain rates. So, these become important because these govern the jet stretching and thinning during electrospinning, right. So, let us look at this a little bit more in detail. Now, we have said that there is a requirement for enough chain entanglements. Now, what is considered enough? So, again recall that we have seen concentration or of the polymer in solution comparable to C star and Ce, where C star is the overlap concentration, where the you see overlap, the chains start to just overlap, the sphere of influence. Much above Ce, you start to, or around Ce and beyond that, you start to get entanglements. And can you recall from our discussions in lecture 14 what these regimes are called? If you've paid careful attention to those lectures, you will be able to immediately recall that these are called the semi-dilute unentangled regimes and semi-dilute entangled regimes, right? Now, we have also seen a plot between specific viscosity and concentration in that lecture, and I am showing here a very similar plot, but now this is a sample plot where the identification of C star and Ce is done using changes in the slope. If you plot it on a log-log scale, typically in the semi-dilute unentangled regime, what you will end up getting is slopes roughly of 1.25, 1.3. So these are ballpark numbers. You will not always get 1.3, but thereabouts. But you will see much higher slopes when you have gone beyond the entanglement concentration, which is the semi-dilute entangle regime, right. So below the CE, you are largely looking at between C star and CE, you are looking at the semi-dilute and unentangled regime, where the slope of this specific viscosity versus concentration plot on a log-log scale will be about 1.3, 1.25, 1.4 thereabouts, and then you see it almost becomes 3 times or more in the semi-dilute entangled regime, and that slope change is sort of how you identify experimentally points such as CE and C star. Now, having identified these, and these can be defined for a polymer in a specific solvent with a specific molar mass of the polymer, that is very important. Once you have that, then now you can ask, in relation to CE, right, which is one way to think about chain entanglements and one objective way to think about chain entanglements, where should I lie for me to get stable fibers, right. So we first note that sufficient entanglements are required to prevent breakup and to produce fibers that are defect free. We will talk just a bit about what are bead free fibers in just a second. And the rule of thumb, typically this is a rule of thumb, this is not an exact rule, this was just enormous amount of empirical evidence is shown that you have to be at least 2 to 2.5 times the critical entanglement concentration for you to be forming stable bead free fibers. So if this is CE, you are somewhere here, right, well beyond CE to be able to electrospin and form bead free fibers. You are 2 to 2.5 times CE concentration to form bead free fibers. And typically the fiber diameter range that is achievable in electrospinning, although these are again ballpark numbers, you can typically have somewhere from say 100 nanometer fiber diameter on the collector to about 10,000 nanometers. So about 0.1 microns to about 10 microns. So several orders of magnitude span in fiber diameter. Of course, you will always have reports that show much less than 100 nanometers or higher than 10 microns, but those are exceptions. The typical useful range and the commonly processed range is about 0.1 to 10 microns. So that is the range we are talking about. This is for the diameter of a single fiber in the non-woven electrospun mesh. And again, I have sort of given you a snapshot of this, but it is important that you recall some of these discussions that we have had about C star, CE and regimes from lecture 14. Now, one question you can ask is, what happens if you are below that 2 to 2.5 times CE, and what happens if you are above 2 to 2.5 times CE? We have already said that if you are 2 to 2.5 times CE, you are going to get bead fibers, right, that do not have defects. But if you are below, what you can end up getting is something called a beads on a string kind of a morphology, or a pearl necklace. Sometimes it is called a pearl necklace morphology, where you see there are fibers and then there are these little beads that show up. Of course, these beads have been elongated a little bit here, and this is a polymer that is very popular, PEO. You see that I have gone from 4% to 6%, and this I believe is 600 kilodalton PEO. And what you see here is, if you are at 6%, you get bead free fibers. But if you are at 4%, you get these beaded fibers, where you have fibers like these and you have stretched beads like these, because the entanglements are not sufficient. And if you are even below 4%, well below 4%, what you might end up getting is more spherical beads, where again you see surface tension effect starts to dominate, right. The idea of sphericity itself comes from surface tension largely, to minimize surface area. So if surface tension effects become dominant, then you start to see more and more spherical beads, and if you are even below that, you will not even see fibers, you will simply see these kinds of spray, just beads, right. So very low concentrations, you will get something like a spray. If you increase the concentration more, you will get something like a beaded fiber. If you increase it further more, you will get these elongated beads, and if you increase it more, you will get full fibers. So that's sort of the progression, going from very low concentrations to concentrations where you get bead free or defect free fibers. So having looked at electrospinnability from a polymer solution perspective, now we will move on to looking at visualization of electrospinning, looking at some videos from real-time visualization of electrospinning, trying to understand how electrospinning happens, and try to look at different segments of the electrospinning cone, jet, etc., and see what we can learn from this. So we'll first start by looking at electrospinning of a PCL solution, where we are going to look at modes in electrospinning, and as the video plays, I will explain what's going on here. So what you have here is vertical electrospinning, and as the video proceeds, the voltage is being ramped up. So initially what you have here is dripping, just largely surface tension makes it a sphere and gravity just pulls it down and just dripping happens. But as you can see, now slowly that drip is now starting to sort of eject a jet. So this is what you would call a droplet with jet, that at further higher voltages transforms into a cone jet, right, as shown here. And if you increase the voltage further, this cone jet will transform to a different mode, right. So what you have so far is a stable cone jet, and the voltage is now still being increased, and as the voltage continues to being increased, you now see that there is something called a rotational mode, where the entire cone and jet starts to rotate, right. That's what you see here. And with further increase in voltage, the single jet will be unable to sustain the electrostatic repulsion, at which point the jet is going to split up, and you see multiple jets that emerge from the cone or the drop, right. So in one video, we have been able to capture the different modes as a function of voltage, going from dripping kind of a mode, which happens at very low voltage, which is still surface tension dominated. Then the cone jet mode, where if you at some point when you get the cone jet mode, if you stop ramping up the voltage and you continue stable electrospinning, the cone and jet is going to get maintained in that same position. You are going to get very stable fibers. Cone jet mode is one of the most preferred stable modes in electrospinning. Further increase in voltage, we saw that you get this rotational kind of a mode, right, where the entire cone jet rotates, and that is a transition sort of a mode from cone jet to multi-jet. With further increase in voltage, what happens is the single jet is unable to, charge density becomes very high, so the single jet is unable to sustain the charges, and the jet starts to split. So you get this multiple jet kind of a mode. Now this is a close-up view of the cone and the jet itself, where you get access to the different kinds of modes. Now you can also look at this zoomed out, and you can look at the entire cone jet and the instabilities that follow. So here what you see is a video where we have essentially it's a zoomed out video, where this part here is what we saw here, right. This is just the cone and the starting portion of the jet, but then you see this video shows, or this video is going to show the entire process that happens, right. So what you have here is the cone followed by the straight jet here, followed by the bending instability here. So you see this bending instability, or the whipping instability as it is called. A lot of work around whipping instability was done by Professor Renneker and Yaren in some very seminal work that they put out back in the day. I will play the video one more time, and what you want to notice is that this is the stable cone jet mode. This is steady state electrospinning, where you have a cone followed by a straight jet. Thereafter what happens is the radial stresses here start to dominate. So, the jet doesn't want to now proceed in the axial direction, but now because the radial stresses start to dominate, the jet starts to do this. And this region is called the whipping or the bending region. It's an instability. Essentially what happens in this region is excessive stretching, as a result of which thinning happens and drying. So this is the very critical region where a lot of the action happens. So I will play the video one more time for you to get a good sense of what is happening in this particular region. So you see this whipping region, this is captured with a high speed camera. You see that there are these coil like features that are characteristic of the bending instability. Now just to give you a sense of the length scales, etc., and the diameter reduction, you're talking about order of magnitude wise, you're talking about roughly about 1 mm here, needle width, needle diameter, give or take. You get thinning here in the cone region itself, then you get thinning in the straight jet region, and a lot more thinning happening in the bending instability. And what's present at the bottom of this process here is the collector, where you're going to get about, let's say, about a micron, right, fiber diameter. So you're going from the width of the cone, roughly about 1 mm to about 1 micron fibers on the collector, or even less. So you're looking at orders of magnitude reduction in diameter of the jet and the fiber. So this is a very important thing to keep in mind. Now, from these kinds of imaging experiments, one can get very interesting insights into jet thinning mechanisms and the cone shapes that are involved in electrospinning. And just as a case in point, shown here are cone shapes in the cone jet mode from different experiments. And what you see here is this work showed that you can have, based on the curvature analysis, you can have concave convex kind of a cone, you can have a pinned concave kind of a cone, you can have an unpinned concave kind of a cone. And if you do image processing algorithms and try to do interface shape fitting, etc., what you can show is you can get access to things like cone length, jet initiation length, and so on. Now these are very useful because the fibers that form on the collector cannot be visualized real time very easily. But if you are able to visualize and measure things like the cone length and features such as the jet initiation length, then you can get very nice insights into how the combination of operating conditions that we saw earlier, namely voltage, flow rate, etc., jointly orchestrate these cone shapes, and how these in turn dictate the fiber thinning and the formation of stable fibers on the collector. And we also show here to contrast this with a droplet jet shape. So this shape is generated with water as the solvent. So this is polymer that is dissolved in water. These are polymers that are dissolved in organic solvents, which have a much lower surface tension. So you see, surface tension of the water ensures that you get something that looks like a droplet. So this would not be traditionally considered a cone jet shape. This would be considered a droplet jet shape. You can still get stable fibers with these, except that because of the high surface tension of the water, you're going to have droplet like shapes. And what you will end up getting eventually at the end of this process is fibers that look like these, roughly about a micron to 2 microns in diameter, depending on what your operating conditions are. So again, just to summarize, this is all work from our lab. what we've been able to show is in situ visualization can provide very interesting insights into the different cone jet feature shapes, cone shapes, jet features, as well as jet thinning mechanisms, right? And how all of that can dictate the properties of the resultant fibers. Now, moving on, we can now talk about some practical aspects of electrospinning, where we can look at electrospinning configurations first. So, what we have seen so far is two different setups. One is a vertical setup, the other is a horizontal setup. But in all those cases, we have seen what is called uniaxial or monoaxial electrospinning, where you have a single polymer solution that is being electrospun. So, you get what is called a monolithic fiber, right? You just get one polymeric fiber, one specific chemistry. You can also have variants of electrospinning by looking at different kinds of spinneret configurations, different kinds of collector configurations, which we are going to look at. So, one variant is what you call side-by-side electrospinning. So, where you do not have one polymer solution anymore, you have two polymer solutions coming side by side, right? Using this kind of a slightly modified inlet, where you have two polymer solutions that come and meet at an orifice and then they get pulled out. So, the resulting fiber, as you can imagine, will have, every fiber will have this Janus-like structure, where this would be one kind of a chemistry, this would be a different kind of a chemistry. So, each of these fibers that forms will be composed of two different chemistries, if you will, right. So, that is one variant of electrospinning. Another variant could be a coaxial, where you have a fiber, where you form a fiber within a fiber structure, right. So, this core shell kind of a fibrous structure, and a TEM image of that is shown here, where essentially you have a needle within a needle, and you have one polymer solution flowing through the inner core and another polymer solution flowing through the annulus, such that what you end up getting is a structure that looks like this, where this is the sheath and this is the core. And these can have a lot of different applications in biomedical engineering, right from tissue engineering to drug delivery to wound dressings and so on. And a more complicated variant of that, of course, is triaxial electrospinning. I mean, if you can do one needle within a needle, you can do more of that. You can write, right? So, in triaxial electrospinning, you have inner core, outer core, and then a sheath, right? So, it's just three different layers as shown here. So, these are just some variants. There are many more. These technologies develop as we speak. So, this is just some classical variants of electrospinning that are widely used and reported. Now, from a collector configuration perspective, as we have already hinted at, if you have a rotating collector that rotates very fast, I have already said that you can have aligned fibers. So, shown here are some examples of configurations that you can have for the collector. One is just a solid flat plate collector, where you will get randomly oriented fibers. You can have a guide wires collector, or a rotating mantle, or a rotating wire drum, or a rotating disc, where you can get different kinds of alignments or patterns, right, depending on the collector configuration. You can even have a liquid bath collector, where the liquid that is present in the bath is a non-solvent. So, you form this cotton candy like structure, and so you start to build sort of a 3D kind of a scaffold through this technique, right, and that can have its own applications. So, this is just to give you some practical insights into how electrospinning variants function, both from a spinneret perspective as well as from a collector perspective. Now, we move on from the electrospinning process itself to what happens on the collector and how we are going to use those fibers, because ultimately we want to be able to connect biomaterial processing to the resultant scaffolds that form and how they can be used in biomedical applications, right. So, shown here again is a snapshot of how the different parameters that we have earlier looked at directly affect the fiber and the mesh properties. So, polymer concentration is just as an example. We have already seen that you will get beads at low concentrations, and as you increase the polymer concentration, you're going to get bead-free fibers, and with further increase, your diameter of the fibers is going to increase. But if you have very, very viscous solutions, then you run into issues with processing, right? That same issue that we have seen before, where viscosity and rheological properties have to be sort of balanced against the processability. Voltage, if you keep increasing the voltage, diameter usually decreases, and many of these effects cannot be generalized. These are commonly seen effects. You can always have exceptions. Not all of them are monotonic effects as well. Sometimes they will decrease and increase depending on the system, but these are some generalized ideas that you can take away from a lecture like this. So if you increase the voltage, you're going to get more and more thinning. So it's not hard to imagine that the fiber diameter is going to go down, but at very high voltages, you can have excessive drying and excessive thinning, which can lead to broken fibers, right? Those are not defect free, those are defective fibers, and that's not something you want to have in your fibers. Flow rate again, with increasing in flow rate, up to a certain point your diameter will increase, but then at very high flow rates again, you will start to see bead-like structures forming that you can also see with very low concentrations. The tip to collector distance, as we have already seen, is going to affect both the drying as well as the electric field strength. So if you don't have a very large tip to collector distance, if you use a very small tip to collector distance, you can have an extremely high electric field strength, but you can also end up not drying the fibers enough. So you can have these wet kind of fibrous mesh that can form. And of course humidity, which is a ambient parameter. So this is a solution parameter. These are operating parameters. This is an ambient parameter. Just one or two quick examples from each category. Very high humidity again will prevent drying, thus resulting in fused fibers with circular pores, right? And that kind of fused fiber morphology, where the fibers are still sort of not fully dried and wet, when they hit the collector, they will sort of flatten out, and you will start to get other kinds of weird shapes like ribbons and fibers that fuse with each other, the pores not being properly formed, etc. And that's a nice segue for us to look at the effect of these things on properties, macrostructural properties such as pore size and porosity. Electrospin meshes are extremely porous. They can be 80-90% porous. In fact, most of it is air, and they're very, very light. But pore size, which is another property, also depends on fiber diameter. So if you have very thick fibers, very large fiber diameters, the fibers will not pack as tightly, leading to larger pores. And if you have very thin fibers, fibers will pack more tightly, leading to smaller pores. You can also imagine that a randomly oriented fibrous mesh, the kind of pore sizes it will have compared to a very tightly aligned fibrous mesh, where the spacing is so small that you will barely see any pores in those kinds of materials. And those are important because fiber diameter, porosity and pore size dictate all kinds of applications and the use of electrospun meshes, particularly in tissue engineering and drug delivery, which are classic biomedical wound healing as well, which are classic biomedical applications of electrospun meshes. So, just to drive home the point, we are seeing here that key features of electrospinning and their impact on the potential application. So, you can get very controllable morphologies with electrospinning, which provides contact guidance cues to cells and can orient their growth and adhesion growth and differentiation. They also, because of the fibrous nature, they can serve as structural mimics of or architectural mimics of the extracellular matrix. We have seen in quite some detail in our lectures on natural biomedical polymers that polymers such as collagen that are found naturally in the extracellular matrix, a lot of it in the connective tissue is in the form of fibers. So, you can sort of think about now a biomimetic approach where you are creating these fibers from electrospinning that can potentially mimic the architecture of collagen. Electrospun fibers also have very high surface to volume ratio, and that can have its own advantages in drug loading and controlling the release profiles of drugs. You can also have very high versatility in polymer choice. So, a lot of different kinds of polymers can be electrospun. This permits a wide range of biomedical applications. And of course, the high porosity and controllable pore sizes provide supports for biological systems. And shown here is just a snapshot of the application diversity. Non-biomedical applications, of course, the major sort of a target sector is filtration, right, for these kinds of membranes. You can also have functional coatings. You can also coat these fibers onto materials to change only the surface properties, which we are going to look at as a dedicated theme later in this course. And of course, classic biomedical applications or clinical applications including drug delivery, tissue engineering, wound healing and biosensing. The applications are enormous, and in a lecture or a course like this, our goal is not to get lost with those applications, but my hope is if you have understood the key concepts underlying electrospinning and the properties of the fibers and the meshes from a lecture like this, you can easily contextualize them when you read the literature for specific applications or when you work with them in specific applications. One very important aspect of electrospinning also is without the use of hot air, you can have extremely high drying rates, and that can have its own positive implications for the preparation of amorphous solid dispersions, locking in both the polymer and the drug in the amorphous state. And as we have seen earlier, that can have a lot of advantages for improving the solubility and bioavailability of poorly soluble drugs. So, there is a lot of applications in the pharma sector as well. And in closing, what we will do is take a quick look at some snapshots of end use cases of both drug release and controlling cell responses very quickly. One example is of a technology that exists is this dual fiber matrix, where you now see here that the two fibers that are there have been dyed with two different dyes, and you see that the two fibers have been co-integrated using a simultaneous electrospinning approach, where you have two spinnerets delivering two independent sets of polymers in the form of fibers onto a common collector, giving you something like this. Now, it turns out that that can have a direct impact on controlling the release of small molecule drugs, where if you control the drug distribution carefully, you can show that you can achieve release profiles that typically match the predicted release profile. You can also have particle fiber composites. Now, one of the challenges with processing proteins, sensitive labile biomolecules through electrospinning is there are two things here that can potentially affect the protein conformation, right? We have talked about protein conformation being very important for protein function. So, if we are delivering therapeutic proteins, two factors in electrospinning have to be carefully accounted for. One is the voltage, the other is the solvent. So, those can have potentially negative consequences on protein conformation. So, one way to sort of think about how to sort of retain the protein structure conformation and stability is to think of particle fiber composites, where these particles made from, let us say, natural polymers can have the protein and integrated further into these fibrous composites, and the circular dichroism spectra show that the protein structure is retained, the secondary structure is retained, the conformation is retained following electrospinning. So, this is another end use case for electrospinning. One is for a small molecule drug, the other is for a protein. You can also have electrospun fibers controlling cell function. For example, here we have changed the fiber alignment going from randomly oriented fibers prepared using let us say a flat plate collector to aligned fibers. You see, right, fibers are highly aligned in one direction using a rotating drum collector. And we showed here that if you culture microglial cells, which are a type of immune cell found in certain kinds of tissues, the orientation of the fiber directly dictates the shape and the aspect ratio of the cells. And with these cells, they have a direct implication on phenotypic function. The shape and the aspect ratio are directly related to phenotypic function. Essentially, here we are looking at polarization one way or the other of these microglial cells towards anti-inflammatory or pro-inflammatory phenotypes under hypoxic conditions. And we showed that changing the alignment can have very beneficial effects for controlling the phenotype of these cells. Another application that combines the drug release end use with controlling biological responses is the use of these drug loaded fibers providing long term release, which can have very positive effects on biological systems. So, shown here is actually the Raman map from a single fiber, right? So this is a Raman imaging that we did on a single fiber. As you go through the fiber, you see that there is drug that is homogeneously distributed throughout the fiber, and this fiber is PLGA, and that it turns out because PLGA is glassy largely at 37 degrees, what you end up getting is because the drug is distributed throughout in the matrix, you get very slow controlled release because the free volume is less. So that directly leads to sort of very slow controlled zero order like release over several weeks, right? This is about 2 months of release, and on less than 50% of the drug is released, right? So this is directly showing that the structure property relationships directly impact the function of the electrospun mesh, and in turn affects the performance, right? So here the effects of dexamethasone, which is the drug here, anti-inflammatory drug, with the fibers is shown to protect cells from hyperglycemic oxidative stress. So just some snapshots of end use cases for electrospun fibers in biomedical engineering, both from drug or protein release perspective as well as the ability to affect specific kinds of biological responses. So I hope with that you get a good sense of how electrospinning, polymer electrospinning particularly operates, and been able to connect some of the concepts we have learned throughout the course to polymer processing using electrospinning. And my hope is if you've been able to understand this, not only will you be able to appreciate the use of electrospun meshes better when you read the literature, but you can also translate some of these concepts that you have read here to other kinds of processing techniques as and when you encounter them. So with that, we will end this lecture.